into web development. So for me, I will if you want to stay here in this chat, in this call, we'll be delving into statistical learning. So this is going to be a kind of short introduction. So you might be able to catch up with uh, Gian's workshop if there's still time. Okay. Start lang at 10 p.m. Exactly. And to those who are still in the call, I would like to remind everyone that this is originally and still is a donation drive for the Typhoon Tino victims. So if you want to donate for the victims, scan the QR code on the screen right now. I believe the proceeds are already up in the thousands. So whoever is receiving the donations will be very happy. And of course, your participation here today is really appreciated. Okay, so before I start, I'll mention lang that uh, for this semester and then after this workshop or tutorial, I'll do three more. So this was the originally planned series of workshops that was presented during the what was it the first GDG like event. And so the next week I think if there's no complications, uh, Sibako, um, we'll be doing parametric versus non-parametric modeling, kind of like an introduction to that. Then after that, we'll do into optimization. Then the last one will be, uh, actually, I forgot. Let me double check. Oh yeah, last one will be principles of resampling, where we'll delve into train and test dataset for better uh, evaluation of your models. So for next semester, it's more going to be more on project-based learning. We'll do a lot. We'll be actually using Google tools now, Vertex AI. Um, we will delve into embedded systems as well with their Edge AI solutions in Google. So for now, it's all theoretical this semester, as I've mentioned before. Next semester, hope you are all excited for uh, hands-on workshops with AI. since then, let's start. So, good evening, everyone. I'm Nick. Let's read. I'm Nick, and I am the AML officer, GDG San Carlos. Today, we will be talking about statistical learning. So, all the references, a lot of the references that I use come from this book, An Introduction to Statistical Learning by James Witten Hasty and Tib Shirani. This is actually free online. You can download this as a PDF file. So yeah, furthermore, this book actually has some hands-on parts where you can actually code in Python, and the book will guide you how to write your first, let's say your first linear regression model, or where you can apply what you've learned in this book into practical aspects of artificial intelligence. So first, let's talk about what is AI. So of course, everyone knows AI by now. I mean, even 5 years ago, everyone knows what AI is. So, but let's talk about AI in more formal terms now. So, artificial intelligence is a technology that captures some pattern in data and tries to predict the future. Last time, I introduced you to Jupyter by creating your first machine learning project. I was able to give you the engineering side of this field through project-based learning, which I think is the best way to learn anything, AI or coding. Well, we didn't learn how to use these tools. We didn't go into how these tools work like magic, because it essentially is magic, right? So, as I mentioned before, next semester we will focus on project-based learning. However, in the following four workshops, we will delve into the theoretical aspects of artificial intelligence. So, today, our initial foray will be into statistical learning. So, what is statistical learning? So, I'm sure you've heard of machine learning and maybe even deep learning. However, what's often missing is the understanding of the foundations beneath these buzzwords. Before algorithms, before code, before models like neural networks, there was this drive of how to learn patterns from data. Um, Statistical learning is not some distinct technology, so it's not it's not different from AI or machine learning. I think for me, or like I think a good way to think about statistical learning is that it's a type of AI model that uses statistics or non-heuristic methods um, to make sense of complex data sets. So I think it's just there so that AI won't be that confusing. It's just a term that gets thrown around to make sense of artificial intelligence. But it's not some distinct technology or something different. It's just some types of machine learning models. So that's exactly what statistical learning answers. It gives us the mathematical lens through which modern AI becomes more than just a collection of tools. So according to the book, no, statistical learning refers to a set of tools that makes a sense of complex data sets. So this is actually the first sentence in the book, but this is kind of vague. So I think a better operational definition would be a set of tools that are based on statistics. Well, in other words, AI. So, but as we've heard before from the name of this tech department, we also have machine learning and deep learning. So what is distinct about statistical learning that we have to talk about it in this introductory workshop? So from this flowchart here, so you can see like statistical learning falls under machine learning, which it does. So essentially, that means that all SL models are ML models. What makes SL models distinct from ML is that they're non-heuristic, which means they rely on explicit mathematical assumptions, probability theory, and statistical principles. In contrast, non-statistical learning models, which I'll be showing you in a bit, uses heuristics or even like biologically inspired strategies. So one example of a non-SL model would be genetic algorithms. It basically uses genetic biological genetics rather to predict, make sense of data and predict patterns. You have swarm optimization, and then you have reinforcement learning. Um, for statistical learning models or methods, of course, you have linear regression, k-nearest neighbors, and um, other models which we'll talk about later. So, how about for now? Let's try to formalize like what we are trying to predict now. Um, we've been talking about predicting the future. We have this powerful, magical technology. You have AI, but we always think of like a lot of the fads going on around right now, where everyone's just trying to use AI for everything. No, even there was this recent paper a few months ago where they used AI to predict the movements of the planets, which is kind of amusing because you have Newton figuring that out like 100 years ago without using computers. So I think it's better to make before going into SL deeply. Let's talk about what are the types of processes and what type of process that we should model with AI. So first, we have deterministic process where output is fully defined by the inputs, so no randomness involved. So essentially, a simple function like f of x, where for example, your y is the height of the ball after you throw it, and your f of x is your ball being thrown off the side of a mountain. So another good example would be from our first episode in Shower Thoughts, where we talked about orbital mechanics, and I gave you the thought experiment of why we shouldn't use AI for predicting the movements of the planets. So essentially, in just one sentence, the answer to that thought experiment is simply that because it's a deterministic process, we shouldn't use AI to solve an already solved problem. So on the other hand, we have stochastic processes. So processes. So these are processes that there is inherent randomness or uncertainty. So think of stocks. Um, what's a good stocks or basically every most real world processes that are done or actioned by human beings are stochastic in nature. So as you can see here, this is an example of a stochastic process, particularly a stochastic differential equation, where this equation has a stochastic term. So all stochastic processes can be modeled and through some function and then a stochastic term. So in this particular process, you have your term as a Brownian motion. So this is actually was used for the Black-Scholes equation, which is an equation that tries to, or actually decently predicts stock, like the stock market. So we have the third process, which we'll definitely not get into, but is just, just a footnote and it's quite interesting. So a chaotic process is deterministic in principle, but extremely sensitive to initial conditions. So if you watch the Netflix show Three Body Problem, where Three Body Problem is a chaotic process where three celestial bodies um, have gravitational effects on each other that are significant, and that they make you unable to predict what the next orbit or next position of the planets are. So right now there is an effort in the CFP community we have of physics informed models where there are people that are trying to predict um what do you call this turbulent flow, which is a chaotic process using AI, artificial intelligence, but that's still in its infancy. So what kind of process are all AI problems? So of course, kind of obvious that all stochastic processes are AI problems. So if you have a stochastic problem, it would likely could be solved or should be solved by an artificial intelligent model. So now let's try to formalize what I've said earlier about stochastic process, where you have a function and then a stochastic term. So all stochastic processes had a function f of x where it's essentially the hidden true function f of x, and then you have your error term epsilon. So your epsilon is your stochastic term, f of x is some hidden um, function that you can't know, that no one would ever know, and that you add on some randomness, and that becomes your system. So um, I'm gonna give you an example. So let's say you are God, and you know you're looking at this data of your years of education and then your salary. So the gray dots here um, signify the amount of salary you're gonna earn given your uh, given your years of education. So imagine you're God, so you know what the trend is like uh how what your salary is going to be uh given your education. So even if you are God, no, you still can't, according to this formalization, you can't predict the future. You can only predict the hidden function, as I termed earlier, the f of x, and this green line is passing through this plot. So um in statistical learning or in artificial intelligence in general, we're always trying to predict, or always trying to make, or we're always trying to model this hidden function f of x. So let's put a linear regression algorithm, and let's try to predict the trend. Now it's in blue, so that's our model, and that's us trying to make sense of this data set. So as you can see, it of course it is kind of similar to your green line, which is your hidden function f of x. And this blue line is what sorry, here we go. Is what what we're using in linear regression if we're trying to model using like Python. This line is what comes out when you're trying to plot it. So the difference in this green line and then this blue line is your error. So it's kind of a bit confusing. So I'm going to go into a different situation. So here, this is a bit more abstract, but you have, this parabolic curve where your hidden line, again, your green line, is this some hidden function that is the best fit, is the most best fit line for your data set. And as humans, we're not gods, so we cannot make the best line of fit or the best prediction of this pattern. So we make something with a bit more error, or with a bit some mistakes and inherent mistakes, because we're mortals, I guess. So in line blue here, you can see that it is a bit what actually using here is a polynomial regression. And as you can see, it does stray a bit away from the green line. So it does indicate that it is not, of course, as accurate, but it is as, it is somewhat like represent our complex data set. So that's the best thing we can do as humans. So it's the same photo. So what are methods in estimating f? So as I've shown earlier, you have your linear regression and then you have your polynomial regression. So of course, how can we estimate F? So, well, you have your machine learning models and you have your deep learning models. But there's something inherent between these models or these methods that can be bent into two types of models. So, first, we have parametric models. So, parametric models assume a specific functional form for f. So, this is what you must always use first. So, in any situation, if you can plot during your exploratory data analysis, um, you must first assume or like look at the data set and then plot it on a Cartesian plane. And if you see that it does have a pattern, let's say if it's linear, linear would be something like looking like this, or quadratic, or something looking like this. So if you know that your process is going to be like that, it's better to use a parametric model. So of course, if your data does change and it deviates from linearity or our initial like assumptions of shape, of course your performance will go down. But the advantage of using parametric models as in equation form right here is that it is very explainable. So you can actually look at, you can do it by hand even, but you can also like use your code and then look at the what we call as coefficients in beta. You have beta sub uh, the letter that looks like the Greek letter B, or beta rather. And for example, in your regression model, this helps you explain how important some variables are. So that's one. So there's a lot of advantages of using parametric models. And also, it is not prone to overfitting, which we will go into the second or the fourth workshop later on. But in most cases, it is better to use a parametric model. So the other type of model, on the other hand, are non-parametric models. So these are models that do not assume a form for f. So let's say you don't even plot your data set. Some data sets cannot be easily plotted, especially if they are high dimensional. So if you try to plot that in a 2D Cartesian plane, what you'll get is just chaos, and like all the dots are just everywhere. You can't even understand where the best line of fit is. So on the other hand, non-parametric models, they don't assume the form for f. So you don't assume a shape because some maybe you can't, or it's just inherent in the process that you don't assume um, the pattern. So most what do you call this? A lot of like hammer solutions come from non-parametric models, especially as we know now, our LLMs, neural networks. These are non-parametric models, and that they can be used for their very different or various of unique circumstances. So, like for example, for neural networks, you can use it for LLMs, which is predicting or like generating text. But then you could also use it to classify images. But then you could also use it to generate pictures. So it's very flexible. So that's like the distinction of non-parametric models, is that you don't have to worry about your data set, and that you just use it right away and then it will solve your problem for you. So here, I want you to guess which is likely the non-parametric model. Is it model A or is it model B? Or which one is the parametric model? So you can leave a chat or whatever. So do you think model A is parametric or non-parametric, or do you think it is model B, which is parametric or non-parametric? So I'll give you a few seconds. So obviously, or not really obviously, but by looking at the regression lines or the lines of fit, you can infer that model A is parametric because it looks linear. On the other hand, model B is not parametric because your line is a bit more squiggly, or it uh, it follows the pattern better than your model A. So from the book, there's this very um, important or informative plot where it compares some famous non-parametric models and some parametric models. So on the top left, you have subset selection and lasso. And then in the bottom right, you have deep learning. So as you go to the top left of this plot, your model is more likely to be a parametric model with, of course, subset selection and lasso being parametric. On the other hand, you go to the bottom right, it's going to be more likely um, non-parametric with deep learning and support vector machines. So what's important to know is that as you go to the bottom right, where your interpretability, or as you go down this ladder, where your interpretability becomes smaller or becomes lower, your flexibility goes up, which means that your model might be able to solve your problems better or even solve it outright. However, problem with that is if there's some sort of problem or you're trying to infer, specifically in data science, right? Trying to have some inference about your data set, like you're trying to learn um, why, Nico, um, why, for example, some models, oh, sorry, for example, why some variables are affecting other variables. Like, for example, like why does height affect the average weight of a person or something like that? These patterns in data sets, you cannot capture this or you cannot interpret this or understand this with non-parametric models that easy. So, as I'm going to reiterate again, it's possible just use a parametric model if your problem is really hard to solve with parametric models. You grab your sledgehammer and use non-parametric models such as deep learning. So, what are the outputs is that F is supposed to produce? So this leads us to one of the fundamental distinctions in statistical learning. If your function outputs a number, that's something we call a regression problem. If F outputs a category or a label, that's a classification problem. So, in other words, if your output variable is quantitative in nature, that's regression. If it's qualitative in nature, that's classification. So, in other words, regardless of whether we use parametric or non-parametric modeling, we must decide what type of prediction task we're solving. This choice determines how we measure the quality of fit or the metrics we use, whether we use accuracy, whether we use root mean squared error, or F1 score, or L1 loss. It all depends on what type of task we're trying to do. So regression is very obvious. For example, you're trying to try to predict the prices of houses. Um, your output are going to be the price of a house, which is a number. So this is by definition a regression problem. It's not inherently, so as I mentioned earlier, um, it doesn't depend on which type of model you're trying to use. So a regression problem could be solved by a neural network, or it could be solved by simple linear regression. So you have classification, where you're trying to classify your data sets. For example, you get a new fruit, like pictures of fruits, and whether you classify it as oranges or apples, that task where we're trying to assign a label or category to that input, which is the fruit, that's called a classification problem. Now, let's look into these 5 questions here, or five like problems. What do you think for the first one, predicting tomorrow's rainfall amount? Do you think this is a regression problem or a classification problem? Well, naturally, since your output is in millimeters, this is a regression problem. Next, number 2, determining whether an email is spam or not is a classification problem. Number 3, estimating the selling price of a condo unit in Cebu, mentioned before, is a regression problem. Identifying species of a flower based on its measurement is it's a classification problem. Predicting the student's final exam score out of 100. Now, this one, let's say your scores are 0, 1, 2, 3 to 10, or to 100. Yes, the output is a number. But you could also say they are categories, 100 categories. So do you think this is a regression problem, or do you think this is a classification problem? So I want your thoughts. If you have some answers, you can write down below. I don't know if someone's actually messaging. So actually, you can use both. In fact, you can use both for all these problems. You can actually use classification or regression for all of these problems. So for example, for number 1, if we're trying to predict the rainfall amount for, let's say, tomorrow, you can bin your initial data, which is in millimeters, and you could bin it in high, medium, and low. Whether there's high amounts of rainfall or low amounts of rainfall. Determining whether an email is spam or not, you could, it looks like it's a classification problem, but you actually could use regression by using your output metric, by using your output as a confidence score. So 1, any value closer to 1 could be, let's say it's spam, or any number closer to 0 is not spam. So since that is a regression problem, you can use, as we've done this before, you can use LLMs or whatever. Estimating the selling price of a condo, you could bin this in high, medium, low, or expensive, medium, and then cheap. For identifying the species of a flower, you could use a confidence score or a regression metric or regression output for this one as well, where for, let's say, you have this setosa. Actually, I forgot the name of the. Let's say you have flower A, flower B, and flower C. For flower C, you could assign a number 3, and for flower A, assign number 1, and then you have another, in your output would be a confidence score, where you try where a number or an output is closer to, let's say, 1, would output or would say that your flower is likely flower A. Now, predicting a student's final exam score could simply be classification, but I think a better solution to this would be regression instead. So let's build into the classification setting. So the goal is to learn a decision rule, or equivalently, some decision boundary. So going back here, this line in the middle, this white line in the middle is a classification boundary. So that is your goal, and that we are trying to make some uh, decision rule that best fits our data set, that we could get the highest performance out of our model. So instead of predicting labels or class probabilities, oh, sorry, instead of predicting exact numerical values, we predict, again, the class labels or class probabilities. So I'm going to give you an example here, an abstract example of a 2D data set. You have feature one for your x-axis and y-axis for feature two. So this, we're going to be using something called Bayesian estimator, where, of course, let's say your feature, your class one is the one in blue, and then the other class is the one in red. Now, these concentric circles around each of these clumps of data are just essentially the variance or the standard deviation of this of the data themselves. So we have outliers outside of our standard deviations, and in the middle you can see that there is one in blue, and that's an outlier. So in classification, this is what we're trying to do. So we're, oh, sorry, it's Bayesian bias classifier rather. So we're trying to create a line that separates your class A and your class B. So this is a bit more specific compared to our simple example earlier. So as you can see, the one separated by the white line, which is your hyperplane, your red or your class B, so the top right, and your class A is at the bottom left. So sometimes, of course, your model can make mistakes, or maybe even every time it could make mistakes. So how do we quantify these mistakes? So this is, I'm sure everyone has heard of accuracy. I mean, it is the metric that everyone's first heard of, even like probably even when you were a kid, when you were like thinking about like how accurate bow and arrow performance is or whatever, if you're like trying to play with miniature bows and arrows. So in this case here in statistics, it also used as a metric for the amount of correct predictions compared to all the predictions that we have. So there are other metrics. Um, Instead of using accuracy here, we could also use the F1 score, which is a bit more, sorry, which is for some people, and which is a better metric in case your data set is imbalanced, which we'll get into that data set imbalance problem later on. But essentially, like majority of your classification metrics, like accuracy, can actually be done by hand. Because it's that's the benefit of using of having classification problem, is that it is simple and it is more interpretable than a regression problem. So what is a regression problem on the other hand? So in a regression problem, you're, as I mentioned before, you're trying to predict some numerical value out of some data set. So it your model tries to approximate the underlying relationship between inputs and outputs. So in this plot here, another regression plot, as you can see, your gray dots is your data set, and then your regression line is in blue. So the red lines or the distances with or the vertical distances uh between your data points and then your regression line is the error. So compared to classification where you have your metric accuracy, where you're just literally counting the number of wrong inferences that your model has done. For example, here you have your let's say you have all this mistaken or misclassified uh, data points that are crossed out. On the other hand, in regression, you're trying to like sum up or like trying to quantify the error by virtue of how far your regression line is on average from your data set. So usually you use RMSE, but you could also use mean squared error for your metric. Again, this is your um, success metric. As earlier, we have accuracy for classification. For regression setting, we could use RMSE. In this case, we're going to be using MSE. So there's actually a beautiful visualization of MSE here. So the the equation itself, for lack of a better term, is counting or like it's finding the sizes or it's summing up the sizes of the areas that we have of the red rectangles or the red squares of all your data points. So you sum it, you sum up all of these red squares, and then after you find the area, that's your mean squared error. So that's essentially what this success metric is doing. So instead of like, for lack of a better term earlier, where we sum up, or I defined it as the vertical distances between your observations and then your regression line. What the mean squared error success metric actually does visually is that it's actually summing up these red rectangles, which are essentially, sorry, excuse me, which which the what do you call this? Which your, let's say your height of this rectangle is the distance from your data point to the vertical distance from your data point to your let me use my mouse here. You can see it. So for example, this data point right here, and this error, this rectangle is representing. So the error here is actually this. Its height is actually its vertical distance from the regression line, and its width or its length actually, although you cannot really see it, is actually the horizontal distance between your regression line. I think a good example would be this one here, where this data point here, where your, of course, the height of this error square, let's call it square error, is again this is the distance, vertical distance to regression line, and its length is the horizontal distance. So this function, this success metric, your mean squared error, is actually just summing up the areas or the areas of these polygons. So another example would be this polynomial, where we're going to be using, or this polynomial looking data set, where we'll be using a polynomial regression to make a best line of fit. So if we visualize the errors, this is what we get. So it's quite big. I think the representation here is not that well is kind of worse than the previous one. But here, um, again, it's just summing up all the squared errors of the data set. The data sets. Oh, sorry, the regression lines, vertical distances and horizontal distances to each observation. So that's really all for this workshop. So, thank you everyone for coming. It was really a short introduction long. I don't want everyone to be overwhelmed by uh, the statistical learning. And personally, I do believe that uh, overwhelming everyone with information is not a good way to learn. So next time we'll be delving into some coding, and where I'll be illustrating, the distinct differences between parametric and non-parametric models. So for now, that's all. So please, once again, donate if you have some, like even like 100 pesos or some cash in your Gcash, or some amount in your Gcash. Just scan this QR code and donate to the victims of Typhoon Tino. So if you have questions, you can just message below, and you can leave anytime if you want to. I'll be staying here until 10:40 or 10:50 for any questions, or if you just want to talk, or if you just want to have some chat, or if you just want to chat, I'll just be here. So if you also, again, if you want to go to GN's, I think it's still ongoing, I'm not sure. To GN's AI integration, the Gemini API, you can still go to that meeting or that workshop in the link and the meeting chat.